So in the last video, we took a look at this idea of approximating areas under curves by using rectangles. And we also saw that these areas would represent specific real-world quantities, maybe like a distance traveled, or we talked about something like an amount of pollution produced by a factory. And we'll see lots of other examples as we move throughout this section and other sections. But what we need to do at this point is to try to figure out some ways that we can more specifically talk about how we are going to plan to use rectangles to approximate our areas. So let's take a look at the following exploration before we generate a good definition for what we're going to be doing. So let's say that the area A is of the region S, which is a region that lies under the graph of a continuous function, can be approximated by using the sum of n approximating rectangles. So take a look here maybe in this picture. You can see that I have over here a function in purple. Let's assume that this is my function right now, f of x. And I have kind of over here a starting value of a and an ending value of b. That's over here on the right side. And so we could see in here very, very easily that there is an area that we could sketch here in this picture, right? Like all the area that's, strange that that won't allow me to shade over this, but we have all of this space that's going to be in here, right? All of this space throughout. That is all going to be the area, and the area A, and I'm interested in attempting to approximate that. So if I wanted to go ahead and approximate that, again, I can squeeze some rectangles in here to attempt to do that. Now, depending on how many rectangles I want to squeeze in, that's going to affect definitely how wide each rectangle can be, right? Here, if I have 3 rectangles, they're all, pretty wide. But if I was going to plug 300 rectangles in here, they're all going to have to get way skinnier. But to figure out exactly how long each of them is going to be is actually a really, really simple task. And what we're going to do first is we're going to notice that since my rectangles are positioned so that way they stretch out horizontally here along the x-axis for their width, then we can talk about the width of them by using a symbol that will be delta x, a change in x. Now, we're going to imagine here that each of our rectangles are ultimately going to have the same width. This doesn't necessarily have to be the case, but for our purposes, it'll just be a lot easier if we always create rectangles with the same width. So if I wanted to figure out how wide a rectangle was going to be, there is a really easy way that I could calculate it. The first thing I could do is just to note how long is my interval in general, right? If my interval is going to be, say, something like 10 units long, and then I want to chop or fit 2 rectangles in there, I could just imagine saying, well, I have a space of 10, and I want to divide that into 2 equal pieces, 10 divided by 2. So what I need to do is to talk about the number or the length of my interval in the numerator and the number of rectangles that I want to use being in my denominator. Now calculating the length of the interval is easy because if my interval starts at a and ends at b, then its length would be represented by b minus a. And if n represents the number of rectangles I'm going to use, then this little formula here could tell me how wide to make each rectangle. Now, if I'm interested in calculating the area of each of these rectangles, I not only need to know their width, but I also need to know how tall the rectangles are. And like we saw in the opening idea, the height of my rectangles will be found by taking a special value of x and plugging it into my function to determine the ultimate height. Now, this value of x could really be anywhere. It could be on the left side, on the right side of the interval, somewhere in between. It doesn't really matter. But what we're going to see here is that I can denote this special x using the symbol x star. So the star just indicating that it's special. I'm also going to give it a subscript of a 1 or a 2 or a 3 so I know kind of which rectangle it belongs to. So as I state here, each rectangle has a height of f of x star, and I'll just put a little I here, where I stands for the numbered rectangle that I'm on. So xi, or x star number 1 is the x for the first rectangle, and x star number 2 is the x for the second rectangle. So I'll say here, just to note that, xi star is any number from the ith subinterval. So it could be any number in there, left side, right side, middle, anywhere in between, it doesn't really matter. So if I have that delta x represents the width of my rectangle, and I take my special xi star and I plug it into the function to get the height, then I could easily see that the area for each individual rectangle would be given by f of xi star, my height, multiplied by my width. And so therefore, if I wanted to go ahead and approximate the total area overall, and I should probably not label that as A since I said A was the area of the total region. But if I then wanted to approximate A, the total area of the total region, then I could say that, well, this would be pretty easy to do. What I would have to do is I would have to take the area for rectangle 1 and add it to the area for rectangle 2 and add it to the area for rectangle 3. And there is an easy way I can repeat or communicate that I'm going to be adding things over and over and over again. And that's with the idea of a summation. I can go ahead and I can state that if I start here at rectangle number 1 and I calculate the area for rectangle number 1, then I can add on the area for rectangle 2, and then I can add on the area for rectangle 3. And remember that the number on top of a summation is going to tell me where I'm stopping. And really, I'm going to stop at whatever the value of n is. So if n is the number of rectangles, then in this case that would be something like a 3. I'm going to keep adding up areas of rectangles until I have no more rectangles to work with. So this is the concept here of what we call a Riemann sum. And we'll summarize this in the definition down below. We'll say here that the net area, or what's also called the signed area of a region, that lies between the x-axis and the graph of a continuous function may be approximated with a Riemann sum, which is exactly what we just stated here. It's using rectangles to approximate the area. And we approximate this by doing exactly what we just talked about up above. We are going to add up areas of a bunch of different rectangles. Notice again that this notation here simply means that we're going to start by computing this formula with I being the value of 1. So that would be f of x1 star times delta x. That's the area for this first rectangle. And then the summation symbol here says, now add and change your value to the value of 2. So that would be x number 2 star times delta x. And that would be the area of the second rectangle. And our goal here would just to be to go on and on and on for as long as we need until we hit the final value of n. So xn star. Now n might be 3 rectangles, could be 30, could be 3 million. It doesn't really matter. As long as I add up all of these, I provide an approximation of the area. Now, there are going to be some special points that ultimately we're going to typically choose for our xi stars. Remember that xi star is really just any number from each of the individual intervals. Now, we're typically going to select the same value, or at least the same position within each interval to pick for our xi star. We have 3 different ways that we're going to possibly do this. We'll either create what we call a left Riemann sum, a right Riemann sum, or a midpoint Riemann sum. In a left Riemann sum, we're going to make xi star actually just be the point that's on the leftmost edge of our intervals. So that would be right here, and right here. I could select all of these to be the points xi star and use those to generate my heights. That would be a left Riemann sum. Now I could also do a right Riemann sum where I'm going to go ahead and start with the right side of each of my intervals and have these be my special points. So notice here in the first interval, my red dot is on the right side. Second interval, x star number 2 would be right here. And on my third interval, x star number 3 would be right there. That would be considered a right Riemann sum. And if I did a midpoint Riemann sum, that would just mean that I'm going to select my special point to be smack dab in the middle of my interval, and I'll use that point to go up and generate the height of my rectangles. And that's kind of like what I have pictured here in the picture up above. Now, when we come to a specific question, you don't have to necessarily choose which one of these you're going to want to do. You'll be instructed to actually use one specifically. And to see kind of how this works, we'll start taking a look at some examples in the next couple of videos that are going to ask us to work with each one of these different types of approximations to kind of see how they work in specific instances.